This lesson is drawing the gradient functions by hand. You'll notice that this is 4.4. There are a few pages before this, but that's an activity that we'll do in class. So drawing the gradient function by hand, we're given an original function and we want to try and draw what the slope function looks like. So just like with our moving man, maybe we should just quickly refer to the moving man. This top graph is the original function. The second graph is the gradient function, showing the gradient at every point. So the idea is, at every point on this top graph, I should be able to draw the tangent line, and the red line will be the slope of all those tangents. So we see in the first example, all these slopes are constant, so we would have marked them constant at the same rate, whatever that rate is, and draw a straight line through them. Whereas in scenario 2, this tangent here compared to the tangent halfway and the end tangent, we can see from the slope of these lines that they're getting steeper. And that's shown down here by this x value, okay, a little bit of a slope. This is more of a slope, so from this value I'll mark a bigger slope. So this y-axis is showing me the slope first as time changes. Finally, the slope gets really steep up here and it keeps increasing. The final one we'll look at to solidify this idea is this final one. See how the slope is positive in these 2 points? Those 2 points, so we mark a positive slope on those 2 points. Right at the top, the slope is completely flat, and that's why the slope here is 0. And then as we continue along the graph, the slope is negative and becomes even more negative, a steeper negative value. So let's try and apply those ideas to our task of drawing the gradient function by hand. In the first function, we're going to have a look at the slope at various points here. So say at -2, I'll put a dot here. What's the slope? Okay, the slope is 0. It's completely flat. So at about -2, I'll mark that the slope is 0. So the original function is sometimes written as f of x, and the gradient is written as f dash of x. Okay, or we can just use displacement time, velocity time in the same way. Sometimes displacement time will be x of t and velocity time will be v of t. Okay, always t on this axis. Okay, but anyway, so what about at x equals 0? What's the slope here? Oh, it's flat as well. Put a point here, and at x equals 2, the slope's still flat. Or t equals 2, whatever we're calling that variable. So if I was to draw the slope of this function versus time, I would have just a flat, it's horrible, a flat line following the horizontal axis. Okay, which is how we describe this graph. We'd say that it is completely flat at all points. Okay, so use that one just with the x notation. Over here, I'll use x of t and v of t, just so we get familiar with these different ways of seeing these graphs. Okay, what about equation 2? How do we describe that slope? Imagine I was standing here, walking up it. I would just experience a constant rate of change. So it doesn't matter if I'm standing at the bottom or at the top. If I'm walking from left to right, my slope is going to be the same. When we're sketching these, we won't actually mark typically what the slope is. I probably typically won't do like a rise over run to calculate the actual value. All I'd note that is, so I can't see it at -2, maybe I'll find it -1. I'll put a point here examine the slope, I notice that it's some positive value. So I'd mark some positive value there. At 0, same thing, mark a point, draw the tangent. Hey, it's that same positive value. So I'll put that same positive value there. And again, I don't get all the way to 2, but I can go to t equals 1. What's the slope here? It's that same value again. So those 3 points, we'll be able to connect them together. Okay, and that will be our gradient function, okay, showing the gradient at any point. So it doesn't matter if I'm at -2, okay, or +2, or 0, or 0.5, regardless of where I was on that original graph, the slope is always going to be the same, okay, whatever this value is. And it'll always just say for us to sketch the gradient function. Very rarely will we be asked to actually put a value on that slope. Okay, so both of these were constant rates of change. Okay, and we can see that in the slope graph. Okay, where the rate of change doesn't change regardless of depending on the x value. Phew, that's close. Okay, so I'll do another one using the f of x notation. So we got f of x and f dash of x for the slope. When we have a variable rate of change, okay, it's can't multitask. Variable rate of change. It's important that we note the key points. So the absolute key point would be this point at x equals 0, where the slope is completely flat. So I'd make sure that I first mark that point at 0 on my slope function. And then I'd look maybe out to where x equals -1 is, and I'd notice that the slope is decreasing. It's a negative slope. So out at -1, okay, I'm going to put some negative slope. What happens as I get further out to say -1.5, out here at -1.5, what's the slope? Well, it looks like it's getting steeper. Okay, it gets steeper, a steeper negative value. I can do the same thing on the positive side. Okay, ooh, that's a positive slope, so I'll mark some positive value. Seems like I'm being strategic with where I'm putting these points. Okay, we'll find out why. And what about it? 1.5. Okay, that slope is getting steeper. So about 1.5. Okay, the slope is getting steeper. So our gradient function there clearly isn't constant. Depending on the x value, I might get a positive slope, or I might get a negative slope, or I might even get a 0 slope in the middle. Okay, that's why it's called a variable rate of change. Final one, it looks like a cubic function. Again, we'll look at the key points. So at that point, just before 1, the slope is 0. So I'm going to make sure that I track this point down, okay, and mark it on my gradient function as a 0. I use the x of t and v of t notation just for funsies. Okay, the other important one is this other place where the slope is also 0. Okay, I'll make sure I mark that down as well. Some people also want to try and say that the slope here is 0, so we should mark it there as 0. But the slope isn't actually 0 at that point. Okay, the slope at this point is some negative value. Okay, I'm not sure exactly what it is, but it's some negative value. what happens between this so I should be more systematic. So always try and start from left to right. I'll leave you for later. So going from left to right, I've got a really steep positive gradient. That's going to gradually get less steep, okay, until it becomes 0. And I can show that with a really steep value, okay, slightly less steep, slightly less steep, slightly less steep, until it gets to 0. From here, I have a negative gradient, okay, that's getting a little bit steeper in the negative direction until it starts to turn around and be flat again. So the steepest part is going to be that part directly in the middle. Okay, the steepest part will be down there, and it goes from being flat to negative to its steepest negative point, okay, and then becomes positive. So we're here. What happens after here? Positive slope, steeper positive slope, really steep positive slope. Positive slope, steeper positive slope, really steep positive slope. Draw these all together. Okay, and I've got my gradient function drawn by hand. Now we're going to do an activity in class tomorrow that'll hopefully help you understand why I drew these two graphs in that particular way. And from that activity, hopefully we'll be able to draw a few conclusions that we can write down in this box before we play around with some of these questions. Okay, bye.